Okay, let's get started. So for the first part is to get the GF255. For this section, I created four functions. So I will explain how the function work and how the result have been tested. The first is the GF255 addition, and this is a simple. So we just use the XOR operation with the A and B. So we will have the value, and it's a bit calculation. And the second part is to calculate the GF255 with the multiplication. So we got the value of a, value b, and also the modulo, and which is an irreducible polynomial, and that is x power 8 plus x power 4 plus x power 3 plus x plus 1. And then we do this operation because we don't want the function throw the exception. So here we gonna make sure we got a remainder and divided by 255, so that will always work. And then we initialize the value, the product equals 0, and then basically the product is we're gonna return the product at the end, and this is a value we need for the multiplication. And for getting the product, we create the loop, and the loop gonna go 8 times from I to range 8. And why we go 8 times? Because because we do it in 8 gigabyte in 8 bytes. So the max of the power, so that will be 8. So we will return the value from the lowest to the highest. All right. So this is so from the A move to the right, we can see this is how it works. And the product equals to product. So this function basically is from the textbook, but it is a variant of the function, and which is which is the and which is the A multiply B and equals to x a 0 So this is a variance. So in this function, and we transfer the value, and also after the b move it to the next part, and the b from and then we have like a two option for the b operation. If the b7 equals 0, and we will do that part. If the b 7, which is means the powers x power 7, they're not 0, and we will do this we will do this operation, and in this operation we will multiply the irreducible polynomial, so we can continue our calculation. And after each loop, and the a value gonna move to the right, and we will get the value and of the product from this function. All right, and later on, and we continue our project, and this is for the getting the GF255 multiplicative inverse, and the first part is to get the highest power value of the polynomial, which is transferred from the decimal a. So from here, and we can see every time the a moves to the right, and we can obtain one more result right there, and after that we will return the result. Okay, so here's the main function for the GF200 and for the invert. And now we have the a, and then we will have the the modulo. We have the modulo, which is also the irreducible polynomial, and we initiate the value g1 equals 1 and g2 equals to 0, and g1 is a value that is inverse, and we will also calculate the g1 using the iteration step by step. So, and g2 is the initial value that need to increase from the 0. All right, so, and there's a while loop. Well, we just want this, and at the end we want the initial value a equals 0. So, and because we use and here the a is the GCD, and we in this function we use extended Euclidean algorithm to find the multiplicative inverse, and the extended Euclidean algorithm computes in addition to the greatest common divisor, and so we will have like a function like this. So right there we will use the function as a equals to t b. Okay, so this is a value that we have. So it's the GCD is supposed to be 1, and sorry, and right there, and we have the value, and we input in value of a, and later on, and we need to have the value of the b. So if the b, we can make sure the b's value can make the GCD equals 1, and then we will have the multiplicative inverse, and that is the main reason why we need to do this why we need to do this this process. So in this process, the j equals to gf degree a minus gf degree v. So that means we change this equation as multiplied by a. They're actually they're minus GCD a and b and equals to t and b. So we do this type and step by step, and after that, and we will have the value of the g1. Okay, and the g1 is the multiplicative inverse. Okay.
Okay, so for the AES functions, we established that the functions that generate the Xbox and inverted Xbox don't need to be generated, since you can store them in a variable, all of the values that you will be using for the shifting rows and the functions inside the rounds. So here, basically, they're defined here as variables as a list, both Xbox and inverted Xbox. And here for the function, these are some of the functions that are required for each of the rounds of the 10 rounds we're gonna execute. So the first one is subbytes, that it takes the current state and replaces it with the value, the SEC value of the Xbox, and replaces it in the state, so it can be manipulated. And the inverted subbytes, it's the same, just it uses the state that is working, and it replaces the value with the inverted Xbox value. So for the inverted shift rows, it inverts the shift rows. It basically, what it does is that what it does is that it shifts to the left. It shifts all the each row, basically at each one by its left. And here it's like a little bit mixing of the functions here, but here basically it does the mixing of the columns. So the mixing of the columns, there are two parts in the step. The first one is the multiplication of the parts in the matrix, and then it explains the multiplication over the Gauss field. And here it makes the add round key that it's simple. It replaces the key that is passed in the established one in the test, and it replaces it in the state. So here is the function that defines a state when it's converted the 16-bit array into a 4x4 matrix, and it's done by taking a text and splitting it into 4 and making it in an array in a list and making a two-dimensional array. And this does the same but the reverse. So this one, this function, we put it in a function, the XOR bytes, so we can execute it when we are executing the mixed columns and the start of a round. So this function is using a standard of padding for the multiple to making a byte of multiple of 16 bytes, the given plaintext. So it's commented that note that if the plaintext size is a multiple of 16, a whole block will be added, and the pad will not do the plaintext will not do the padding. And the same for the unpadding. So we created a class in which we implemented the core functions of the AES standard. So we first make a constructor here to take the key of the master key and then subtract it into each of the subkeys that we're going to use in each of the rounds. So for the expanded key, it makes the key into a matrix first and then is divided by 4, because we are going to put it in a matrix. And then it will iterate and will form every of the subkeys